Forget everything you think you know about atoms. That cute little model you learned in high school, those billiard balls orbiting a nucleus like a miniature solar system, is not just wrong. It's fundamentally misleading. An atom is not a physical object. It's a probability cloud, a mathematical construct that defies every single intuition you've ever had about things and matter. What you consider solid is nothing more than a quantum hallucination, a persistent illusion created by information interactions at scales so minute that classical physics shatters like cheap glass. Quantum mechanics doesn't just modify our understanding of the atom, it obliterates it. When we look closely, and I mean truly closely, not through the lens of comfortable classical assumptions, what we find is a realm of pure probability. Where particles aren't locations, but probability amplitudes, where position and momentum play a quantum dance that laughs at your naive deterministic worldview. Consider the electron. In your classical mind, you imagine it as a tiny sphere spinning around a nucleus. Wrong. The electron exists simultaneously everywhere and nowhere. It's a wave function, a mathematical description of potential states. When you measure it, you don't capture a definite object. You force a collapse of possibilities into a momentary reality. This isn't philosophical poetry. This is quantum mechanics, the most precise description of reality humanity has ever constructed. Every time you think you understand what's happening, quantum mechanics reveals another layer of complexity that makes your previous model look like a child's crayon drawing. Quantum field theory pushes this even further. Fields are the fundamental reality. Particles are mere excitations, local disturbances in an underlying quantum landscape. Mass, charge, spin, these aren't intrinsic properties. They're emergent phenomena arising from field interactions. Most people leave when things get uncomfortable. You stay. That means you're different. Truth isn't for everyone. It's for those willing to question everything. If you're one of them, subscribe, like this video, and tell me in the comments what reality you're ready to challenge next. Let's keep thinking beyond the surface. Take energy. In classical physics, energy is a straightforward quantity. In quantum mechanics, energy becomes a probabilistic concept. The ground state of a quantum system isn't zero energy, but a zero-point energy, a fundamental quantum uncertainty that prevents absolute stillness. Even in perfect vacuum, quantum fields fluctuate, creating and annihilating virtual particles in a ceaseless quantum dance. Quantum indeterminacy isn't a bug, it's a feature of reality. The more precisely you measure a particle's position, the less precisely you can know its momentum. This isn't a limitation of measurement. It's a fundamental property of quantum systems. Reality at its most fundamental level is probabilistic, not deterministic. Entanglement shatters our classical notions of locality and causality. Particles that have interacted can remain instantaneously correlated across vast distances, defying our understanding of information transfer. Einstein called this spooky action at a distance, but it's not a quirk. It's a fundamental quantum communication mechanism that suggests information might be more fundamental than matter or energy. The quantum world reveals that what we perceive as empty space is actually a seething quantum foam of virtual particles constantly emerging and annihilating. Vacuum isn't nothing. It's a dynamic quantum state with inherent energy and information potential. The boundary between something and nothing becomes meaningless at the quantum scale. Quantum mechanics transforms our understanding from a universe of objects to a universe of interconnected possibilities, a fundamental reimagining of reality itself. Classical intuition crumbles when confronted with the computational nature of quantum mechanics, where reality is not a fixed landscape, but a continuous negotiation of probabilities. Forget your comfortable notion of information. In quantum mechanics, information isn't something you collect. It's the fundamental fabric of reality itself. The no-hiding theorem reveals a profound truth. Quantum information is never destroyed. It's transformed, distributed, and coded, but never truly lost. Your classical intuition screams that this is impossible. Quantum mechanics laughs at your limited understanding. Entropy isn't just a measure of disorder. It's a computational process that reveals the fundamental architecture of reality. When you look at a system, you're not just observing. You're participating in a complex information negotiation that restructures reality at its most fundamental level. Black holes become the ultimate information processors, not cosmic garbage dumps. Every bit of information that falls into a black hole isn't annihilated. It's encoded on the event horizon, a two-dimensional information membrane that preserves the quantum state of everything that crosses its boundary. The holographic principle isn't a metaphor. It's a literal description of how reality constructs itself. Quantum decoherence demonstrates how the weird quantum world transforms into the seemingly stable classical reality we experience. It's not magic. It's a systematic loss of quantum coherence through environmental interactions. Your sense of a stable, predictable reality is an emergent phenomenon, a statistical average of countless quantum negotiations. Quantum computing exposes the computational nature of reality. Classical bits are binary, 0 or 1. Quantum bits exist in superposition, representing multiple states simultaneously. This isn't a computational trick. It's a fundamental reimagining of information processing that reveals how quantum mechanics transcends classical computational limitations. Consider quantum error correction, a process that seems impossible in classical systems. Quantum information can be preserved and protected through intricate encoding mechanisms that distribute quantum states across multiple particles. Information doesn't just exist. It negotiates its own preservation, creating redundancy and resilience at the quantum scale. The quantum no-cloning theorem reveals a fundamental limit of information. You cannot create an exact copy of an unknown quantum state. This isn't a technological limitation. It's a fundamental property of quantum information that prevents perfect replication. Your classical intuition of copying and duplicating breaks down at the quantum scale. Gauge symmetry reveals something even more profound about information. The fundamental laws of physics remain unchanged under certain transformations. Symmetries aren't just mathematical abstractions. They're computational principles that constrain and define how information flows and transforms in reality. Quantum entanglement demonstrates that information is fundamentally non-local. Particles that have interacted can remain instantaneously correlated across vast distances, defying classical notions of information transfer. This isn't just strange. It suggests that information might be more fundamental than matter or energy, a basic property of reality itself. The quantum Zeno effect shows how observation can freeze quantum systems. On continuous measurement can prevent a quantum system from changing, effectively stopping time at the quantum scale. Your classical understanding of time as a smooth, continuous flow shatters when confronted with quantum mechanics. Quantum field theory suggests that particles aren't fundamental. Fields are. Particles are mere excitations, local concentrations of energy and information in an underlying quantum landscape. Mass, charge, spin. These aren't intrinsic properties, they're emergent phenomena arising from information interactions. The universe isn't a collection of objects. It's a computational system, a continuous process of information negotiation and transformation. Every measurement doesn't just reveal a pre-existing reality. It participates in creating that reality, a recursive loop where the observer and the observed are intimately, inescapably linked. Quantum mechanics reveals that reality is fundamentally participatory. Information isn't something passive. It's an active, dynamic process that constantly reconstructs our understanding of existence. Every certainty is provisional. Every model is a temporary approximation, waiting to be refined, challenged, and transformed. If this challenged how you see reality, follow the channel and tell me what you think. Reality is not what you think it is. Causality is not a linear narrative. It's a quantum negotiation that defies every classical assumption about time, space, and connection. Quantum mechanics obliterates the comfortable story of cause and effect. In the quantum realm, events don't simply follow each other in neat, predictable sequences. They emerge from a complex landscape of probability, where the future doesn't just depend on the past, it negotiates with multiple potential paths simultaneously. The quantum delayed choice experiment destroys classical notions of causality. Imagine a photon sent through a double-slit apparatus. The act of measurement, which can happen after the photon has supposedly already traveled, retroactively determines its previous behavior. Your classical intuition of time as a unidirectional arrow, shattered. Quantum non-locality reveals a universe far more interconnected than your limited perception can comprehend. Entangled particles communicate instantaneously across vast distances, violating every classical understanding of information transfer. This isn't just weird. It's a fundamental statement about the fabric of reality. Consider the quantum Zeno effect, a phenomenon that demonstrates how observation can literally freeze quantum systems. Continuous measurement prevents a quantum system from changing, effectively suspending time at the quantum scale. Your smooth, continuous understanding of temporal progression collapses into a probabilistic dance of potential states. Gauge theories expose the computational nature of fundamental interactions. Symmetries aren't just mathematical abstractions. They're the fundamental programming language of reality. The way fundamental forces interact isn't a mechanical process. It's an intricate information negotiation that defines the very structure of existence. Quantum field theory reveals that particles are not fundamental. Particles are mere excitations. local concentrations of energy and information emerging from an underlying quantum landscape. Mass, charge, spin. These aren't intrinsic properties. They're emergent phenomena arising from complex information interactions. The holographic principle suggests something even more radical. The entire three-dimensional volume of space might be encoded on a two-dimensional boundary. Reality isn't a solid, fixed landscape. It's a dynamic information projection, constantly negotiating its own existence. Black hole thermodynamics exposes the computational nature of spacetime. The event horizon isn't a boundary. It's an information membrane that preserves the quantum state of everything that crosses it. Information is never destroyed. It's transformed, encoded, or redistributed, a fundamental property more basic than matter or energy. Quantum decoherence explains the transition from quantum weirdness to classical predictability. It's not magic. It's a systematic loss of quantum coherence through environmental interactions. Your sense of a stable, predictable reality is an emergent phenomenon, a statistical average of countless quantum negotiations. The quantum no-cloning theorem reveals a fundamental limit of information. You cannot create an exact copy of an unknown quantum state. This isn't a technological limitation. It's a fundamental property of quantum information that prevents perfect replication. Your classical intuition of copying and duplicating breaks down at the quantum scale. Emergent spacetime suggests that space and time are not fundamental. They're computational outcomes of more basic quantum interactions. Imagine reality not as a stage where things happen, but as a continuous computational process of information generation and transformation. Quantum computing demonstrates a computational model of reality that transcends classical limitations. Quantum bits exist in superposition, representing multiple states simultaneously. This isn't a computational trick. It's a fundamental reimagining of information processing that reveals how quantum mechanics reconstructs our understanding of computation itself. Entropy isn't just disorder. It's a fundamental information process that reveals the computational architecture of reality. When you observe a system, you're not just passively recording, you're actively participating in a complex information negotiation that restructures reality at its most fundamental level. The quantum realm reveals that observation is not passive. It's a dynamic interaction that creates reality. Each measurement doesn't simply reveal a pre-existing state. It participates in constructing that state, a recursive loop where the observer and the observed are intimately, inescapably linked. Information conservation becomes a fundamental principle. The quantum no-hiding theorem demonstrates that information about a quantum system is never truly lost, just distributed or transformed. Reality is an intricate information network, constantly negotiating its own existence. Quantum mechanics dismantles your comfortable classical narratives. It reveals a universe that is fundamentally probabilistic, interconnected, and computational. Every certainty is provisional. Every understanding is a temporary model waiting to be refined, challenged, and transformed. The universe is not a collection of objects. It's a continuous information processing system, a quantum computational mechanism that constantly reconstructs its own understanding of existence. Classical intuition crumbles when confronted with the radical computational nature of quantum mechanics. Reality is a negotiation. Existence is a process. And quantum mechanics is our most sophisticated lens into the fundamental nature of this continuous probabilistic reconstruction of reality. If this challenged how you see reality, follow the channel and tell me what you think. Forget everything you think you know about atoms. Your high school model of neat little billiard balls orbiting a nucleus is not just wrong. It's a catastrophic misrepresentation of reality that reveals how profoundly limited human intuition is when confronting the quantum realm. An atom is not a thing. It's a computational process, a dynamic information network that negotiates its own existence moment by moment. What you perceive as solid matter is nothing more than a persistent quantum hallucination, a statistical average of probability waves that dance at scales so minute that classical physics becomes a laughable simplification. Let's deconstruct the atom ruthlessly. In your classical understanding, an electron orbits a nucleus like a planet around a sun. Quantum mechanics obliterates this naive picture. The electron doesn't orbit. It exists as a probability cloud, a mathematical construct that simultaneously occupies multiple positions. When you measure it, you don't capture a definite object. You force a collapse of infinite possibilities into a momentary fragile reality. The atomic nucleus itself is not a solid object. It's a quantum negotiation of protons and neutrons held together by fundamental forces that are themselves probabilistic information exchanges. The strong nuclear force isn't a mechanical binding. It's an intricate quantum communication mechanism that reveals how information sits at the foundation of what we call matter. Quantum uncertainty is not a limitation. It's a fundamental feature of reality. The more precisely you try to measure an electron's position, the less precisely you can know its momentum. This isn't a measurement problem. It's a fundamental statement about the nature of existence. Particles are not objects. They are potential states, mathematical descriptions of possible interactions. Consider the quantum weirdness of atomic structure. Electron orbitals are not paths. They are probability distributions, complex mathematical functions that describe where an electron might be found. These orbitals are not physical locations. They are information landscapes where quantum potential manifests. The periodic table is not a catalog of objects. It's a computational map of quantum information interactions. Each element is a unique quantum signature, a specific configuration of probability waves that negotiate their existence through fundamental quantum principles. Atomic properties emerge from quantum information exchanges, not from classical mechanical interactions. Quantum tunneling reveals the truly bizarre nature of atomic interactions. Classically, a particle shouldn't be able to pass through an energy barrier it doesn't have enough energy to overcome. Quantum mechanics says, watch me. Electrons can literally teleport through barriers, a process fundamental to nuclear fusion in stars and quantum computing technologies. The atom's mass is not an intrinsic property. It's an emergent phenomenon arising from quantum field interactions. Mass is what happens when fundamental quantum fields negotiate their existence. The Higgs field doesn't just give particles mass. It's a quantum information processor that defines how energy transforms into what we perceive as matter. Quantum entanglement demonstrates that atoms are not isolated objects. They are interconnected information networks. Atoms that have interacted can remain instantaneously correlated across vast distances, defying classical notions of locality. An atom is not a discrete entity. It's a node in a vast, instantaneous quantum communication network. Atomic spectral lines are not just pretty colors. They are quantum fingerprints, precise information signatures that reveal how electrons transition between quantum states. Each spectral line is a quantum communication, a precise information exchange that tells us how quantum systems negotiate their energy states. The quantum nature of atoms means that what we consider solid is an illusion. Matter is 99.99999% empty space with tiny quantum particles dancing in probabilistic relationships. Solidity is an emergent phenomenon arising from electromagnetic interactions at the quantum scale, a statistical average of quantum negotiations. Quantum field theory reveals that atoms are not fundamental. Fields are. Atoms are local excitations in quantum fields, temporary concentrations of energy and information. The electron isn't a tiny ball that exists in an orbital. It's a quantum excitation, a dynamic information process that constantly negotiates its existence. The atomic clocks, our most precise timekeeping devices, operate on quantum principles. They don't measure time. They count quantum transitions, revealing how time itself emerges from quantum information exchanges. Your classical understanding of time as a smooth, continuous flow shatters when confronted with quantum atomic behavior. The quantum Zeno effect shows how observation can freeze atomic systems. Continuous measurement can prevent an atom from changing, effectively suspending quantum transitions. Your comfortable notion of cause and effect collapses into a probabilistic dance of potential atomic states. Quantum decoherence explains how the weird quantum world of atoms transforms into the seemingly stable classical reality we experience. It's not magic. It's a systematic loss of quantum coherence through environmental interactions. Your sense of a stable, predictable atomic world is an emergent phenomenon, a statistical average of countless quantum negotiations. Atoms are not objects. They are computational processes, dynamic information networks that constantly reconstruct their own existence. Classical intuition crumbles when confronted with the radical computational nature of atomic quantum mechanics. Reality is a negotiation. Existence is a process. And the atom is our most sophisticated window into the fundamental probabilistic reconstruction of reality. If this challenged how you see reality, follow the channel and tell me what you think.